Hello, Namaskar. Welcome to chemistry here, and today we will take again the temperature dependence of rate of reaction. Yesterday in the previous video we also discussed the same thing, but today we will discuss the temperature dependence on the basis of concept of activation energy. Okay, in the previous video what we have discussed, the temperature coefficient and Arrhenius equation, and accordingly we discussed the temperature dependence, how the Arrhenius equation we can use for this topic, and how we can use the temperature coefficient for deciding the effect of temperature on rate of reaction and consequently the rate constant. Okay, so if we take the concept of activation energy, then first of all what we should know, what is activation energy. Okay, so whenever a chemical reaction takes place, what is the requirement for happening that reaction, means what are the conditions so that a reactant converts into product. For that what is required is the reactant needs to the minimum or certain amount of energy first, so that it will increase at a maximum level of energy, and that is what is called its threshold energy. Okay, the total energy of reactant at the time of conversion into product. So first the reactant gets some extra amount of energy, okay, to get at that maximum level of energy. It means what, there is always a barrier for reactant to convert into product, and if a reactant is converting into product, that reactant has to pass that energy barrier. Okay, and what is that energy barrier? The maximum amount of energy which a reactant should have if it is getting into product. Okay, so reactant needs to get some extra energy, some potential energy they already have. The reactant already have some energy, certain amount of energy. Okay, that is called its potential energy. Okay, then it needs some extra energy. Okay, and that some extra energy is called actually the activation energy. Okay, according to Arrhenius, what is the concept is, each reactant or reactant should collide each other, okay, to get that extra energy and convert into product. Okay, suppose we are considering a reaction between hydrogen and iodine. Okay, so what Arrhenius says is, this hydrogen and iodine should collide first. Okay, and molecule of reactant collide with each other to form an unstable intermediate, and unstable intermediate will be formed by this collision. Okay, and that unstable intermediate will convert into product. So coming up to that unstable intermediate, because this intermediate will be of higher energy. Okay, so for coming or for formation of that unstable intermediate, some extra energy is required for reactant, and that extra energy is called activation energy. That extra energy is called activation energy. Graphically, if we want to understand, suppose these are the reactant, okay, and they have already this much energy. Okay, now if they are colliding with each other according to Arrhenius, with the effect of those collisions, they will get some of molecule will get some extra energy, and they will reach up to this level. At this level they will form such type of a intermediate, and that intermediate is also called activated complex. Okay, and this activated complex again then get into product or convert into product to form hydrogen iodide. Okay, so this extra energy, this much extra energy is required for reactant to convert into product, and this is what is called activation energy. Okay, and now at this level, this total energy of reactant, okay, the total energy of reactant is called threshold energy. Okay, the energy difference between product and reactant is called enthalpy of reaction or heat of reaction. Okay, so accordingly, if the energy of product is less than reactant, then it will be an exothermic reaction, and if the energy of product is more than reactant, then it will be an endothermic reaction. So according to this graph, all the molecule in the reacting species do not have the same kinetic energy, that we know. If a reaction is taking place, then all the molecules do not have same kinetic energy. Okay, it means what? They will not strike with the same speed. Okay, their speed will be different. So some of collisions may be effective, or some of collisions may not be effective. Effective means what? If collision results into product, that collision is called an effective collision. Okay, since the behavior of molecule is difficult to predict precisely, okay, behavior of a single molecule in a reaction mixture cannot be concluded how much its kinetic energy or like that. So what is done? Statistics is used. Okay, and there are two scientists. One is Ludwig Boltzmann and another one is James Clerk Maxwell. It means Boltzmann and Maxwell. They used statistics to predict the behavior of molecules. Okay, means how the molecules are getting kinetic energy, how many molecules are getting sufficient kinetic energy to convert into product, and they used a term that is fraction of molecules. Okay, fraction of molecules means the ratio between the molecule having energy E means these are the number of molecules which have the kinetic energy E. Okay, and NT is what? The total number of molecules. So this ratio is called fraction of a molecule. Okay, this ratio is called fraction of a molecule. So what happens there is, if we are increasing the kinetic energy by increasing temperature, or by shaking, or by radiation, or whatever the device we are using to increase the kinetic energy. So if the kinetic energy is increased, then the fraction of molecules with kinetic energy E increases. First it increases, okay, it will reach at a maximum, means this is the kinetic energy. Okay, this is the kinetic energy where the fraction of molecules, okay, this one is maximum, and this kinetic energy is called most probable kinetic energy. This kinetic energy is called most probable kinetic energy. So according to Boltzmann Maxwell, the distribution of a kinetic energy may be described by plotting the fraction of molecule, that is Ne upon Nt, with a given kinetic energy. Okay, this is fraction of a molecule with a given kinetic energy and kinetic energy. So that is what we extrapolated a graph according to Boltzmann and this one Maxwell. Okay, so the peak of this curve is called most probable kinetic energy. Okay, the peak of this curve is called most probable kinetic energy, because the statistics is used here. So that is why the term fraction of molecule has come into picture. Okay, now see, each reaction has a definite value of activation energy, means for each reaction this activation energy will be having a definite value, a definite numerical value, means if the molecule will get this much extra energy, that is what is called activation energy. In simple words, activation energy can be defined as the extra energy required for reactant to convert into product is called activation energy. This is the simple definition of activation energy. So since it is observed that the activation energy for different reaction is different, and hence the fraction of total collisions which are effective will be also different. What it is said, each reaction has a definite value of activation energy, and this activation energy decides that a fraction of total collisions which are effective. Effective means the collision which convert the reactant into product. So that collision is called an effective collision. Lower the activation energy, of course faster will be reaction, and if higher the activation energy, of course the rate of reaction will be slower, because if this energy gap is more, then the effective collisions will be less, am I right? And then the conversion of product from reactant will be less. Okay, so activation energy decides what will be the rate of reaction, whether it will be a fast reaction or a slow reaction. Okay, so on the basis of probability consideration, okay, again the probability consideration on the basis of statistics, this is a graph. Okay, this is a graph at two different temperature. One is at T degrees Celsius and another one is at T plus 10 degrees Celsius. Yesterday we also discussed that temperature coefficient. So according to Boltzmann and Maxwell distribution curve, this is Boltzmann Maxwell distribution curve, which is in between fraction of molecule and kinetic energy. Okay, so this is a graph at T degree Celsius temperature. Okay, suppose this is activation energy. Okay, means if the molecules are getting this much energy, kinetic energy, then only they will convert into product. Am I right? This much kinetic energy. Okay, this is fraction of molecule. So at T degree Celsius, this is the graph, and this is the fraction which is converting into product. Fraction of molecules at a T degree Celsius. Okay, not here. This don't confuse that this is kinetic energy. This is fraction of molecules, not the kinetic energy. Okay, energy is this one. Okay, suppose here the kinetic energy is reaching. Okay, in this graph there is no like this potential energy like here. Okay, suppose what we are supposing that here, if the molecule are getting this much kinetic energy, then they will get activation energy equal to activation energy, and they will convert into product. So at this temperature, this much was the fraction. Now if you are increasing the temperature as 10 degrees Celsius, then what is happening, the graph is getting flatter. Okay, means the peak of graph is getting lower. It means it is getting broader, because the total area under graph will be same. The total area under graph will be same. So if it is getting flatter, it is getting broader, then what will be the result of this broadening? This extra area, okay, this much extra area, okay, is the area which is getting into product, which is converting into product. Okay, so on increasing 10 degrees Celsius temperature, this much extra fraction of molecule will convert into product, and this is clear from the graph. Okay, and this is showing that on increasing 10 degrees Celsius temperature, the fraction is getting almost doubled, and that is what we have discussed in the case of temperature coefficient. Okay, a closer look to this graph clearly reveals that the rate of reaction becomes double on increasing 10 degrees Celsius temperature. Thus, increasing the temperature increase the fraction of molecule actually which are converting into product. Okay, means the number of effective collision is increasing. If we will increase temperature, of course the kinetic energy of molecules will increase. If the kinetic energy of molecule will increase, the speed of molecule will increase, the collisions will be faster, and if the collision will be faster, the number of effective collisions will be more, and if the number of effective molecules will be more, then of course the number of product molecule will be more. Okay, and hence by this distribution curve, okay, Boltzmann distribution curve reveals that the temperature dependency of a reactant which are getting into product, and we can understand this very clearly that this extra fraction is observed when the temperature is increased 10 degree Celsius. Fractions means that part of molecules which are converting into product. So that part is increasing. Okay, that part is increasing. Okay, 10 degree difference is there. So this is how we can understand on the basis of a concept of activation energy, that how the fraction of molecule is increasing on increasing the temperature. Okay, what is most probable kinetic energy? The kinetic energy where the fraction of molecule is maximum. So that is what is called most probable kinetic energy. Okay, so kinetic in this discussion, what is conclusion? That activation energy actually decides how the fraction of molecule is increasing. Okay, because if it will be here, so the fraction will be greater, fraction will be larger. Suppose here if the activation energy is reached, then of course the fraction of product molecule will be greater. Am I right? So this decides that how much reactant will convert into product. So this is what is called concept of activation energy, and on the basis of our this one Boltzmann distribution curve, we can understand this results. If we consider our Arrhenius equation, then in case of Arrhenius equation, e raised power minus E A upon RT, this is equal to what? This is equal to fraction of molecules. If we consider Arrhenius equation, then in Arrhenius equation, this is the fraction of molecules. Okay, so if this will increase, means the product will increase. Okay, so this you take care please. Sometime it is asked what is fraction of molecules in Arrhenius equation. So this is what the fraction of molecule in Arrhenius equation. Now let us understand what is the effect of catalyst on rate of reaction. Effect of a catalyst on rate of reaction. So first we need to understand what is catalyst. Catalyst is a substance which is used in so many chemical reaction to increase their rate of reaction. Okay, means it is a substance which is used in chemical reaction to increase their rate of reaction, or what we can say to complete the reaction in less time. Okay, and the amount of catalyst which is required is very less, and end of the reaction the catalyst regenerates. It means this is the substance which itself does not take part in chemical reaction and does not appear in the product. Okay, it will regenerate it. Okay, so this such type of substance are called a catalyst. And how this catalyst does this? How a catalyst can increase the rate of reaction? Okay, so what catalyst does in a chemical reaction? It provides an alternate path of lesser kinetic energy. This is how we can understand the effect of catalyst on rate of a reaction. What catalyst does? Catalyst provide an alternative path of less activation energy for that reaction, and hence if the activation energy will be less, of course rate of reaction will be more. Okay, so this is how we can understand the effect of a catalyst on rate of reaction. What is catalyst? Catalyst is a substance which increases the rate of reaction and regenerate itself at the end of that reaction. Okay, that is what is a catalyst is. If a substance decreases the rate of reaction, sometimes it may happen that a substance decreasing the rate of reaction. Okay, so for that substance the word used is inhibitor. What? Inhibitor. Okay, so one is catalyst which increases rate of reaction and another one is inhibitor which decreases rate of reaction. Another term which is used is the promoter. Okay, one another term which is used when we study catalyst is promoter. So promoter is what? Promoter is actually a substance which increases the efficiency of a catalyst. Promoter is what? The substance which increases the efficiency of a catalyst. Okay, it does not take part in a chemical reaction. Okay, but increases the efficiency of catalyst. Promoter. Another term which is used, poison. Poison is a substance which decreases the efficiency of a catalyst. Decreases the efficiency of a catalyst, that is called poison. Understand? So this is how we can understand the effect of a catalyst. It provides an alternative path of a lesser kinetic activation energy and hence the rate of reaction increases. Okay, effect of catalyst. So that's all for the day. Effect of temperature and how the concept of activation energy works. Okay, how the temperature coefficient again can be understood on the basis of distribution curve. Okay, what is most probable kinetic energy, what is effect of catalyst, that is what we have tried to understand. Okay, so thanks for watching, have a nice day.